In this problem, we're interested in temperature and buoyancy changes due to condensation. Now, this might be important if you're interested in the energetics of thunderstorms or interested in the energetics of hurricanes. So the ultimate goal of this problem is to calculate the change in the buoyant force that's enacted on a given parcel of air due to condensation. And we're going to solve this in 5 parts. We're going to look at the energy released due to condensation. We're going to look at how this could heat the air. We're going to analyze the changes in density, the changes in volume, and then finally the change in the buoyant force. So let's say we have a moist parcel of air. It has volume of 1 meter cube. It has a density of 1 kilogram per meter cube. And it has a water fraction, meaning that in this parcel of air, there are 1.5 times 10 to the minus 2 kilograms of water per kilogram of this parcel of air. And let's say that this parcel of air is surrounded by dry air with a density of rho naught equals 1 kilogram per meter cube. So our first task is to calculate as this moist air condenses and rains out its water, how much energy is released by the rain. And we're going to say that this happens at T1 equals 15 degrees Celsius. That's the condensation temperature of the rain in this moist parcel of air. Okay, so we're interested in determining how much energy is released by the rain. So first we need to know the latent heat of water. How much energy is released due to the phase change from a gaseous state to a condensed liquid state? Well, the latent heat of water is 2.5 times 10 to the 6th joules per kilogram. So for every kilogram of water in this phase change, it releases 2.5 times 10 to the 6 joules. We have joules, and that's the unit of energy that we want to solve this part, which means we need to know the mass of the water released so that we can multiply it by the latent heat and cancel out this kilogram term and just end up with joules. Okay, so what is the mass of the water? Well, we have a density, right? So density has units of mass divided by volume, right? And we have a volume, so we can say that the mass of the water equals ρ1, which is 1 kilogram per meter cube, times V1, which is just 1 meter cube. And because these two terms represent the combined parcel of both air and water, we need to assess the fraction of water contained in this parcel. So we just multiply it by this fraction F water, right? Okay, and so when we do that, we just end up with M water, the mass of the water, equals 0.015 kilograms. Okay, so we can just say that J released, or the energy released in joules, equals L water times M water. Okay, and when we carry out this calculation, we find that we're releasing 3.75 times 10 to the 4th joules of energy. And that's all of the energy released just by raining out all the water in this one parcel of air. So we just calculated that the energy released in joules from the condensation of all of the rain in this parcel of air is 3.75 times 10 to the 4 joules. What if all of this energy went into heating the air? How warm would the air get? Okay, So let's say that we know the heat capacity of the air. Let's say it's 1,000 joules per kilogram Kelvin. Okay, and we just calculated that the mass of the water released is 1.5 times 10 to the minus 2 kilograms, which means that the mass of the air in this parcel must be the difference between rho 1 V1 minus m water equals 0.985 kilograms, right? Okay, so we want to figure out the delta T, or the change in temperature due to condensation, assuming that all the energy released goes into nothing more than heating the air. Okay, so this just turns into a unit cancellation problem. Notice that we have the unit of delta T that we want here in the CP term, degrees Kelvin, which means we need to get rid of the joules term and we need to get rid of the kilogram term. Well, lucky for us, we know the mass of the air that's being heated because we just found it, and we know the energy being put into this mass of air, which we just calculated. It's the same as the energy released. Okay, so let's just do our units term, units cancellation. So we want degrees Kelvin, right? Okay, so if we do the unit cancellation, units of joules must be on top, and then we need joules kilogram Kelvin here, and we need kilograms here. So the joules cancel, the kilograms cancel, and we invert, and we end up with units of degrees Kelvin. Okay, so that must mean that our formula must be T2 equals T1, because remember, the condensation happens at 15 degrees Celsius. So there's already a temperature associated with this parcel of air. And so any temperature change must be in addition to this original temperature. And these units correspond to J released divided by the heat capacity, Cp, times the mass of the air. Okay. And when we carry out this calculation, we get a T2 term of 53.07 degrees Celsius, which is very unrealistic because that's very hot. And so not all energy related to condensation goes into the air. It's probably some fraction, but definitely not all of it, because we would be in a lot of trouble if this simplifying assumption was actually physical. But as a thought exercise, this is the answer that you get. Now we want to determine the density change of this parcel of air due to condensation, both due to the loss of the moisture in this parcel of air, but also the change in temperature. So to determine the new density of this parcel of air, we're going to use something called Charles' law, which basically says that density equals some constant K divided by temperature. So there's an inverse relationship between density and temperature in this simple model. So we can say that rho 1 must be K over T1, and rho 2, the new density, must be equal to K over T2. All right. And so that must mean that rho 1 divided by rho 2 equals, and when we divide these two, the K's cancel out and the T's flip position, and we end up with T2 divided by T1. So that must mean, rearranging this equation, we find that rho 2 equals rho 1 T1 over T2. Well, we know the original density. It was 1 kilogram per meter cubed. We know the original temperature. Things condensed at 15 degrees Celsius. And we know T2 because we just calculated it, 53.07 degrees Kelvin. And so when we carry out this calculation, we get a new density, rho 2 equals 0.883 kilograms per meter cube. So that's the density change due to condensation and the subsequent heating that we just found of this parcel of air. So we just found that the density change due to condensation of this parcel of air, the new density is 0.883 kilometers per meter cube. So that must mean that the temperature or the volume has also changed, right? We want to find the new volume of this parcel of air. Okay, well, we know that density equals mass divided by volume. So that must mean that V rho equals M, and that must mean that V equals M divided by rho. Okay. Well, we know the mass of the air that's been heated in this parcel, right? We found it up here above. We know that the mass here is just the M air, and that's 0.985 kilograms. And we just found the new density, right? So that's rho 2. And when you carry out this calculation, you end up with a new volume of 1.12 meters cubed. So that behaves exactly as we expect. We heat the air expands, and the mass of the air has remained constant. We haven't changed the mass of the air. So we heat the air expands, the density decreases. And so this is the new volume of our air parcel. So finally, we arrive here at our objective. The change in buoyant force that's enacted on this parcel of air due to condensation. All right, so remember, we have this moist air parcel and a surrounding dry air mass. And the surrounding dry air mass, because there's a density differential between the dry air mass and the wet air mass, the dry air mass enacts a buoyant force onto this air parcel. Okay, so we're interested in figuring out what the buoyant force changes between before this moist air parcel condensed and after it condensed. Okay, so what was the buoyant force originally? Well, the buoyant force originally was just the original volume of this air parcel, 1 meter cubed, times the density differential between this air parcel and the surrounding dry air mass, which is rho 1 minus rho naught minus rho 1, rho naught being 1.2 kilogram per meter cube, and rho 1 being 1 kilogram per meter cube, times g, the gravitational acceleration, 9.8 meters per second squared. Okay, so when we carry out this calculation, we'll say that F buoyant naught, or the original buoyant force before condensation, equals, and we plug in these values, and we get 3.48 newtons. Okay. So what about the buoyant force after condensation? Let's call this F buoyant, I guess we'll call it FB1. All right. Well, we need to rearrange this formula a little bit because things have changed. It would now be V2 times the density differential, rho naught minus rho 2 times g. So this is the volume of this expanded air parcel due to condensation times the density differential between the surrounding dry air mass and the air mass that has just condensed its moisture and has been heated subsequently, times the gravitational acceleration. And when you plug in the values that we've previously calculated, you get 1.96 newtons. Okay, so how have things changed? Well, the percent change, let's call this delta percent. The percent change equals FB naught minus FB1 divided by FB1 times 100. And the factor is 77.55%. we have a decrease in the buoyant force due to condensation and due to heating. So there's not as much lift acting on this air parcel after it's condensed all its moisture. And that has implications, of course, for hurricanes, for storms, for tornadoes. And so this is an important concept to understand. So we have accomplished all of our objectives. We have a basic sense of understanding about how temperature and buoyancy and density and volume and mass change when an air parcel rains out its moisture and the surrounding air mass has to adapt the force that it's enacting to keep a nice equilibrium balance. So that's it for this video, and I'll see you next time.